Okay, welcome to Physics 110 Lab. This week we are going to be discussing optics, and refraction in lenses is the specific topic within optics. There's really two main parts to this, and the first part, we're going to verify something known as Snell's law. We're going to use a piece of glass, so we'll talk about that first, and then afterwards we'll come back and follow up with the discussion of lenses and focusing images. So what I'm going to do first is head over and just give you a few details about the refraction aspect. And before I do that, let me point out what we mean by refraction. You've seen this before. The classic experiment would be to take a look at, let's see if I can show you over to the side. This is, if I take a pencil and place this pencil in water, the pencil appears broken is one of the ways that it's usually described, but the basic idea is that you can tell that the pencil looks different and it's not in line anymore. Notice how here right by my finger it's not in line with the one up above. It's actually magnified a little bit too here based on due to the glass and the water effect. But the basic idea here is that light is traveling at a different speed through the glass as well as the water. And so when it effectively bounces off or reflects off that surface and comes back to us, we call that change in speed, or the change in direction that occurs there, we call it refraction. So what we're going to look for is to figure out, for a particular type of material, how much does light bend for that material? So that's known as the index of refraction. We're going to do it for this piece of glass. We're going to try to determine what the index of refraction is through this glass. So let's go take a look at the notes over here from the lab manual. And if I had a piece of glass, let's say if I place this glass here, then we could represent light, and we can think of it in terms of a ray, so a beam of light, so to speak, is an easy way to think about it to begin with. And it comes in and interacts with the change in the surface from what would be air out here to glass in here, and the light will bend. In this case, because the index of refraction would be higher here for glass, it will actually bend towards what we call the normal. In other words, notice this line that's going through the center here. That line is perpendicular to the surface, and so we measure the angle from perpendicular to the surface, or this interface here, relative to the ray, as opposed to from the parallel to the surface. Okay, so that's a key point there to keep in mind when you make the measurements. All right, so when it bends towards the inside, what we're going to do is we're going to try to line up a couple of pins. So we're going to place these are push pins with a little colored head on top of them. We're going to place one here very close right up against the surface, and then I'm going to place one out here. That's going to represent the starting and ending lines for a ray of light effectively. And what I'm going to try to do is line those two up along a particular angle, and I can measure this angle and know what that is. Then I'm going to look from this side into the glass, and I'm going to look to see to line up those 2 points. Then I'm going to use, and I'll be looking through the glass, so I'm seeing the image of the 2 pins, and I'm going to place a third pin on this side of the glass to line up with the image I see here. Then that way I can go from this point where I have the image of the 2, what I would see actually, but I would draw from the interface here a line straight out to wherever I put my pin out here that I saw it, and I can measure that angle. Okay, so I'm going to first start by drawing some of the known angles. And in your lab manual, there would be a piece of paper that's given here with a line through it, so a very simple one. I'm going to place a point right here, okay, just so I have a reference mark for where I would like to measure my angles from. And I'm going to take this protractor, and I'm going to place the center marking right on that, and I'm going to try to line up the 0 on each side, or the 180, whichever your perspective here. And their recommendation, if I can line this up well, I'll try to be careful. I have a camera in my way, but I'll do the best job I can here. So the recommendation is to do 5 different angles, and so they say 10 and 20 are good starting points, but they don't mean the 10 here, because remember, we're going from this point here. So this is the, I'll put maybe a little inverted T here to represent the orthogonal mark, but that's dead on. So I'm measuring from that point. So you'll notice here that if this was 90, then if I move over here to this point here out to the 100, then that would be 10 degrees, okay, for my incoming. Then I can mark one for 20 degrees, 30. And they also recommend here 45, as well as 50 degrees. And the reason we don't go any further is because it would actually be the width of the glass is not very large. It would be difficult to see those, okay? So I have those markings. Now to make it easy for me to place these, I'm going to go ahead and draw some straight lines through this from this point out here. Okay, a little off there, but okay, so this will allow me to put pin. I'm going to place a pin here and leave it there. And I'm going to place a pin here, make a measurement, then move the pin here, and I'll move it to each successive angle and make the measurements on this side over here. And I'll mark those and notate which one they are so we can make the measurements later. Okay, so let's go back over to the table. And you'll see I'm going to place the paper here, okay? And I have this foam block, and I'm going to place the glass on this line that we saw earlier, okay? So maybe I can switch to this camera view. I don't know if that'll help a lot, but we'll see if that helps a little bit. So I have this lined up with this line here, okay? So I'm going to take a couple of pins. I'll take maybe this pink pin, place it right here. And then let's take the yellow one and let's place it anywhere along this line of 10 degrees. Okay, so it's going to look kind of like this. So we're using this foam board, which makes it a little easier to push the pins into this. And so lots of cute writing. I see Dylan was here. I guess he forgot that he graduated high school. But if we're going to make these measurements, it's going to be a little hard to see. I'm going to try to show this to the camera as best I can when I look through these, but for a moment I'm going to have to, I'll probably turn it this way, and I will try to look down along the edge of the table so that you maybe can perhaps see exactly what I'm doing here a little bit. Okay, so I'm looking through the glass, and I'm moving my head around just a little bit. I don't think you can see that part of it. Move out here just a little bit. Okay, so I'm moving around, and I can see where those two, I'm looking at the image, in other words, where I see the pink and the yellow head pins over here, where they line up, and then I'm placing my pin there, okay, based on where I see the images line up for me, okay? So I can rotate it like this, and I can see that they're out of alignment. When I do it here, I see the real pin here matching with the images of what I see of the other two through the glass, okay? So let me grab something to write with here, and I'll make a mark that this was for, I'll just put maybe number 1. So these are my different angles, 3, 4, and 5. So my number 1 pin is here. Okay, so now I'm going to move this guy over to the 20-degree line, okay? And I'll do the same thing. I can remove this pin now since I have the hole marked so I know where it's at. Now I'm going to turn this until they line up and place it right there. That will be number 2. Okay, let's move this over here. Repeat. Okay, mark number 3. Okay, I think I'll change the camera angle for us real quick so that you can see this a little differently and watch what I'm doing, perhaps if that other way doesn't work. So let's move this over to the 45 now. So again, I'm looking through and I am trying to find, there it is, there's the image of the yellow and the pink lined up together. And I'm going to place this pin in line with what I see through the glass. So there's my fourth one, and finally we'll go to 50. There. Okay, so there are 5 different measurements that I have made, or 5 different trials. So now what we'll do is we'll go back over and actually make the measurements. Can take the glass off now, can remove the pins. And we're going to take this guy back over and look over on the camera here. Okay. So again, before I use, you'll notice that if I place the protractor here, I can't quite line up the holes here. So the easiest thing to do first is to place my pencil right here at where I had the pin marked. Okay. This way it'll be easy to tell where the line intersects with the protractor. Other than being able to read the protractor, of course, these are not critical lines. So now I'm going to line this back up just like I did before. Place the center mark on the where I had that pin here. And then I'm going to read off. So it looks like I'm at about 5, 6. It's about 6 degrees there, almost. But this would be 13 degrees. Okay. And let's see, the next one is going to be right here, which is going to be, that would be 19 degrees. And then we've got 28 degrees. And then finally 32. Okay. All right, so that should have all of them. So we got the degrees down. I'll give those numbers to you. And we will then be able to, you'll correlate the 10 degree to the 6 degree mark. Looking back at the lab manual, this equation here is Snell's law. So we're going to say that the index of refraction of air, we are giving that to you as 1. And the theta 1 that they list here is going to be your incident angle. So that would correspond to, say, the 10, 20, 30, 45, or 50 that we had as the incident or incoming ray angle. And then we have the refracted angle that we're measuring over here, theta 2. And that's going to be the numbers that I was just writing down here, the measured ones that were refracted, the 6, 13, 19, and so on. And those are corresponding to the incident rays that were at the top. Okay. So what you will do then is take, let's say, for example, the 10 degree mark and the 6 degree refracted. So 10 degrees would be theta 1, 6 degrees would be theta 2. N1 is air, which we've given you that, and you simply solve for N2. So that's what we're looking for here is N2. We want to find out what that is. Do that for all 5 sets of measurements of the different angles that we picked that you have here. And then once you find N for each of those sets, you're going to find the average of that and report it back to us. And expect you to get somewhere in the ballpark of about 1.5, maybe a little above or below, depending on the glass that would be there. But so, all right, now we're going to move on to the next section, okay, where we're going to talk about lenses. And there is another data table here that I'm going to fill out as we work through these. There are, as you see, 4 different tables or 4 different areas to report. So we have 4 essential experiments here that we're going to do, but they're all related to one another. So let's take a quick look since we're here already and look at the lab manual and see that if you had a lens that's called a converging lens, what that means is that if you had two rays of light, this would be some object, they're just drawing something here. That could have been like the pen we had a moment ago that we were using. But just some object that's here, and you have the parallel ray will be traveling, parallel meaning like if you drew a straight line through the center from where the object starts and through the center of the lens, then a parallel ray would be one that goes parallel to that. What you would find is that it would refract through the converging lens, but it will go towards and converge. The reason it's called converging is we're converging towards some point over here. If you drew one that went from this point straight through the center of the lens, so it crosses this, what we call the optical axis and the center of the lens, then it would pass straight through, okay? You could draw more rays where you bring them in at an angle and then see where it comes back out. But the trick to that would be to understand what's called the focal point, okay? So a focal point, every lens would have a focal point. If this object was some infinite distance away, okay, so as far away as you could get, the further away this object gets, the closer these lines that you have here will meet at the same point, okay, or along this same axis. So we're going to do this in a moment where we're going to have some object that is effectively at infinity, and we're going to find where the image that we see of that object after it's gone through the lens, and we'll measure the distance, and that will tell us the focal point, okay? But we're also going to do it a second step where we're going to place the object at a much shorter distance, so a non-infinite distance, and we're going to then measure the image distance. In other words, we'll be able to measure the distance from here to here. That will be the object distance. In other words, how far away is the object? Then we'll measure from here, the center of the lens, out to where we see the image on a screen, and that will be the image distance, okay? And then we'll be able to calculate what the focal point is, and we can compare those two ideas between the one that's at a finite object distance and an infinite object distance. So we'll look at both of those, okay? We're also going to look at the idea of interchanging some of these values. I'll talk about that in a moment as well. But before we can discuss that, we actually need to go back and look at the equations. And so, let's see. I have to find this. Sorry, it took me a second here to find where I'm at. There it is. All right, so here's the equation, equation 3. And you'll see that this equation says 1 over F equals 1 over SO plus 1 over SI. Now they tell you that SO, S sub O, is the object distance. In other words, the distance of the object from the lens. That means if you measure from the center of the lens to this object, what is this linear distance here, okay? Then you see SI, which is the image distance. Again, very similar. We're going to see an image, and this will make a lot more sense when I show you in just a moment. But you're going to see an image distance. We'll measure from here to get the image distance. All right? The F is the focal length. Okay, so in this equation, I would plug in the distance that I measure, how far away the object is itself, and then I would plug in the image distance, and then I would be able to calculate F. Now notice this is 1 over, so you have to do 1 over this plus 1 over that, and then once you get those answers, you would have to invert that once again to get the actual focal length, okay? All right, so let's take a look at those first, and then we'll come back and talk about the very last one, which is the telescope, okay? So we'll be able to go through these first sets pretty quickly. All right. So I'm going to move a few of these things out of the way here for us and show you what we have in front of us. Okay, so this is a screen. All right. So we're going to be able to try to focus an image onto this. I have a set of lenses here, of which we have both a red lens, what they call a red lens, and a yellow lens. What they mean by that is simply that there is a colored dot on these, so you're able to tell. The difference actually is the thickness. So this is a much thicker lens, okay, than this, if you look at between the two. So they're both converging lenses. That means they'll both do that first thing. There is a such thing as a diverging lens. As an example of that, it is thinner in the middle than it is at the edges. So when rays of light enter this, they'll actually diverge and move away. Okay, and so there's some unique properties for that. But today we're going to focus on the converging lenses. So the thicker the lens, the more the rays of light will bend, and so they'll refract more at a greater angle. And so the focal point for this is going to be much shorter than it will for the yellow lens. Okay, so we're going to use those two ideas together to help us understand, or to be able to find some of these images. Okay, so let me set up the cameras for a second so that you will be able to see what's going on. Okay, so I've readjusted the cameras, and what I'm hoping you'll be able to see now is that I'm going to show you, looking in this direction, there is a window that's over there, okay? So I'm going to use that as an object. So if you look through the window, you'll see the student center there, you'll see Benson off in the distance, probably see people walking by, some cars, trees. All of those things are extremely far away, okay? So that distance compared to this distance, whatever I end up setting this at, but this is going to be a relatively short distance compared to the distance from here, whereas I'm going to place my lens, all the way out to whatever's out there. Let's say Benston. Okay, that's a very large distance relative to this. And as you might understand from basic math, that as you look at a larger distance, okay, so in other words, as if your object distance here, SO, becomes a very, very large number, 1 divided by a very large number gives you a very small number. So the bigger this number is, then what you're going to find then is that F will be equal to S sub I if this becomes effectively infinity. Okay? So that's what we're going to do in this first experiment. All right, so I probably need to turn the lights off a little bit for you to be able to see this. I'm also going to have a camera I'm focused on being able to see the point here. What we're going to do is I'm going to adjust this lens so the light coming from the window is going to refract through this lens and it's going to form an image on this screen, okay? So we'll work on doing that. Let me go ahead and turn the lights down and you should be able to see with all the natural light. Okay, and I think I'm going to go ahead and change to the second camera so that you can see up close. Okay, so here's the image. I'll try to give it a chance to focus. Now, I'm going to slide. And eventually, we shall start to see. There it is. So it's blowing out the camera a little bit. It's pretty bright. Okay, so I think what I'm going to do. Okay, so I'm going to make a change to what's known as the iris on this camera. So in other words, how much light I'm allowing in, because it's adjusting for all of the light in the room. So as I turn this down, now you should be able to begin to see the image that's formed. Okay. So you can see Benson there, some trees, and so not bad. Okay, so I'm going to take a measurement of that. So we'll come back over to me here, and I'm going to measure simply with a meter stick the distance here. 5 point, let's say about 5.3. So I'm going to record that value down in centimeters. Okay, so now we're going to repeat the same experiment, except this time using the yellow lens. So I'm going to slide this out because I do expect the focal length to be longer on the yellow lens because this is a thinner lens. So I'm going to place that here. And let me go ahead and let you see the second camera there. There we go. Very, very nice. So I'm going to turn this up just a little bit here. Help us see it. I think it gets a little bit dark on the computer screen there, but you can see me walk through. And so that should give you a good idea of the image. So kind of cool if you've never seen that before. All right, you see people walking by. If only they knew they were going to be, their shadows would be recorded a very long time. Okay, so I see about 14.5 centimeters, so I'll record that value. Okay, we're done with that part. All right, so next up, I am going to change the setup so that we will be able to, we're going to be able to look at a different object. Remember I said we were going to do a finite distance, so instead of using something like Benson and the people outside, we're going to switch over and use this object. I'm going to light this up. This will be a little F, and we'll be able to try to focus that on the screen at a finite distance here, okay? All right, so magic of photography, we are back now with everything rearranged. Okay, so hopefully you'll be able to see this. What I'm going to do is I have this light that I showed you earlier that's got little LEDs in the shape of an F. This is to help us determine if it's inverted, if it's a reverse mirror image, things like that. Not too concerned with that today, other than we're just simply looking for the focal length, okay? So we're going to use that same equation we did earlier, except this time we don't get to use a infinite object distance to make the equation very simple. This time we actually have to make a little bit of a calculation, but still not difficult. So I'm going to be measuring the distance from these lights to the center of the lens. So this will be my object distance. Instead of Benson, this has become my object. Then I'm going to look at the screen over here, and the distance from the center of the lens to this will be my image distance, okay? So I'm going to switch over one of the other cameras here and start to move this lens in and see if you can see where it becomes a focused F. So I'm going to move it past it beyond and try to find the most focused version of that. That looks pretty good to me there. So hopefully you can see this on the camera. It'll be a little difficult there with all the different lighting conditions, but you should be able to see an F that is inverted, okay, in both planes. All right, so what I need to do then is I am going to measure the distance from here to here. That's about 16.4. This is for red, so that's my image distance is 16.4. The object distance, measuring, it'd be easier actually to do it probably. I guess I'll do it this way. We call that about 17.7, or sorry, 37.7. Okay, so at that point you're going to plug it into the equation. So you now know what your object distance and your image distance are. You'll plug it in the equation, do the inverse of both, add them together, and then the inverse of that answer to tell you what the focal length is. Then you'll be able to compare that back to what you found in what we found earlier in step number 1. Okay. All right. So let's go ahead and switch it over to yellow. In this case, I know it's going to be a longer focal length, so I am going to spread these out just a bit. Okay, and I can tell that I'm pretty close, and so if you take a look at this camera, you'll see that kind of, maybe at that point right there, I think I found one. All right, so as I focus in over there on that, maybe we'll also take a look and see what it looks like as well here. Yeah, not quite as well focused. I think it's a little easier to see at that place. To be able to tell, I've definitely got an F there, okay, so an inverted F. Of course, it doesn't look like an F in that bit, but so let's go ahead and then again we're going to measure. I do want to point out one other thing in a moment about this, but let me switch back over so you can see the measurement. And what we're going to do is we're going to look at a different way to focus this. So let's go back over here to 20, that's about 20.4 for my image distance, and then my object distance is going to be I'm going to call that about 40, a little more difficult there, but about 48.7. 48.7. Okay, so I want to show you a second. If you take a look here, you've got remember this is the image distance, this is the object distance. All right, so we're going to go back over and take a look at the equation again. Now, mathematically, and remember in physics, we're typically trying to understand the world and explain what happens with it and be able to predict things that happen. So one of the ways to do that exactly is to use mathematics. And so here we have an equation that tells us that if I have the image distance and the object distance, and I invert both and add them together to find the focal length, right? Now, looking at this equation, what would happen if you did not know, if I did a poor job explaining this to you, and you mistakenly inserted the value for SO into SI here, and in other words, you switched SO and SI in terms of the numbers I gave you? Would you still get the correct answer? After looking at that for a moment, hopefully your answer was yes. You would get the same answer. And so your object distance and your image distance can be interchanged and you still calculate the correct focal length. Okay, if that happens mathematically, then it better happen in the real world, okay? Because if not, there's something wrong with this equation. So let's go back and take a look at this here. And so I want to show you that I've got you remember we had the focused image, okay? So if we take a quick look at that, there was our focused image. All right, so I am now going to take the same distance, which we had, which was about, let's see, it was what, 20.4, all right? So that's my image distance. I'm going to write that down, 20.4, my image distance for position 1, okay? And then I'm going to take the same distance that I measured a while ago and make sure it's still the same, about 48.7, yep, sounds good. Okay, now we're going to find a new position, all right? So in other words, the distance from here to here, I should be able to, in the equation, switch these two values and get the correct answer for the focal distance. Okay, well, what if I do that physically? Let's take this value and switch it with this value. In other words, let's physically move this guy from here back over to about here somewhere. And let me show you on the other camera, guess what we get? A focused image. Now, note that equation does not say anything at all. It'd be a little hard for me to get just the focal length. These higher ones are a little bit tougher. But it does not say anything at all about the size of the image, okay? So you'll notice that is much larger. So the size here is definitely larger than the other, but that equation just simply says the focal length and the object distance and the image distance. That's the relationship between them. It does not tell you anything about the size, okay? We'll come back to the thing about size in just a moment. Okay, so let me record these values. That'll be for step 3, and you'll be able to verify that in fact this works. This was always kind of an interesting one to do, so I'm going to do this and say, my value is a little higher this time, got about 49. This time I'm about right at 20.0. Okay. All right, so I've recorded those values there. You'll be able to look that over. All right, now, I'm going to shut all this down and we're going to move back to our to the final step, which is magnification. And let's go ahead and turn off the red F here. We're going to remove that and we're going to build a telescope. Okay, we won't need the screen anymore because we're going to use our eye. And so we're going to come over and I'll make some changes to the setup and also to the cameras to help us be able to see this. And we're then going to use 2 lenses to generate a very simplistic telescope, okay? Okay, so let's take a look at step 4 in the exercises. We're going to build a simple telescope. We've removed the screen and the light source you saw a moment ago, and a second lens holder we've added. So in other words, we're going to take 2 lenses and we're going to place those lenses along the same axis so we can see them. And we're going to be able to calculate what the magnification would be. So let me give you a quick overview of what that looks like. Go over to this side. So all I've done here is I've removed the screen and everything else, and I've placed 2 lens holders, and I have 2 lenses here. Okay, let's talk about which lens I want to place where and why. So the first lens is going to act to take the light coming from outside. Okay, so I'm going to focus on Benson in this case, on the bricks there, and it's going to bend and converge to that point. The parallel rays coming from far away are going to focus on the focal point. They pass through that point, and then this is going to collect the lines that have passed through. And then they're going to bend as well, and we would be able to kind of draw this out, and I think there's a diagram we'll look and see. But anyway, to draw out the simple telescope. But basically, we're going to use these 2 lenses to converge a image on my eye, and then I'm going to try to show you that with the camera. Okay, so the 2 lenses together will hopefully be able to give us those. Got a couple shots to show you how that's going to work, but let's first look at what we want to use. So the equation here, you notice, says capital M, which is magnification. Okay, the magnification you want to use, this has FO and FE, 2 more things to look at and decide what they are. FO is the focal length of the objective lens, okay? So focal length is what F means, and then the O is objective lens, okay? And then the E is for the eyepiece lens. Now, I guess I could give you extra points, but don't have a good way to do that. If you can tell me which one of these do you think goes closer to the object, and which one do you think goes closer to your eye? So what we want then is we're going to have a lens closer to our eye and a lens closer to the object. And to calculate what the magnification is, all we simply have to do is plug in the known focal length of those 2 lenses. Okay, so we had 2 lenses, the red and the yellow lens. We've calculated their focal lengths, and we figured out that the focal length for the Y is a larger value. In other words, a longer focal length, okay? And the red was for had the shorter focal length, okay? So which of those 2 do we want to be closer to the object? All right, well, since magnification, we would like this value to be large, right? So in order to make that happen, this needs to be the bigger number, and FE needs to be the smaller number. The smaller I make this, the larger that is, and of course the converse is true for the FO. So that means I need the yellow lens to be here and the red lens to be here. That means the yellow lens needs to be my objective. In other words, my lens closer to the object, and the eyepiece needs to be the red closer to my eye. Okay? All right, so let's make the measurements here and record them down, and we'll be finished. All right, so I'm going to take these over, and I have the yellow lens here in this holder, and I have the red lens here in this holder. I'm going to take them over to this table, and we're going to, and I'll show you how I'm going to go about doing it. Then I'll bring it back and try to show you the image there quickly to close out, okay? So I'm bringing this closer over here so that I will be able to see. And I'm going to move this, I'm keeping the red lens in the one place because that's much easier for me to keep that still and with my eye, because it's a very, very small diameter lens. So therefore, if I move my eye around, you might even be able to see this on the camera, you may see the reflection of the light going around my face. So the more I do that, the more difficult it is. And I think I'm pretty satisfied with that. I have the bricks in Benson focused pretty well. They're very clear looking through here. So now I'm going to bring this back over. And what I want to measure is the distance from here to here, okay? So I'm going to go ahead and do that. And it is exactly, well, not quite, but it's about 20, let's say 20.2 2. Okay, so I'm going to write that down here. Now you'll notice in the on the paper, let me point what I'm talking about here. I've written the distance between lenses. You will not calculate anything with this number. This is simply for us to write down what they are. Now what we expect is for those two focal lengths to line up on top of each other. So in other words, I would expect for the focal length of my objective and the focal length of my eyepiece to add to give me this value here, okay? So you will write down the focal length of the objective lens and the focal length of the eyepiece. How do you get those? Well, you've done it two different ways before. You've done it with the calculated where we had the finite object distance. In other words, we used the red F. And then you have the one we did it for the red and yellow here. What you could do, what I would suggest is take this value and do the average, and then do this value and this value and do the average, and that's what you could write down here for your focal lengths, because those were two different measurements and you can give the average of those. Then you simply plug these two values into that equation to get your magnification. Okay, so very straightforward. All right, so finally, what I'm going to do is I'm going to try to line this up, okay, on the camera, and what I would like to do is show you a focused image just to prove to you kind of what it looks like. It's going to be a little difficult here, but you of course can see out here, you can see the building out there, but what we're going to look at is, let's see if I can line this up. You should be able to see the bricks there. It's going to be very, very difficult because the closer I bring this in, the higher up the axis it gets, but maybe I can raise the camera up just a little bit. And you should be able to see that tree is actually in focus. And if I move this over, you can see the bricks there. So again, you see how narrow of a axis we have to look through there because those lenses are small diameter, but you should be able to see they're very well in focus, okay? All right, so that finishes up the lab for this week. So a little long, but hope you enjoyed it and hope you learned a little something, okay? So check with your TAs for any questions you have, and thanks for a good semester and good luck.